Internal Corrosion Direct Assessment Methodology for Normally Dry Gas Pipelines, DG-ICDA. Assessing corrosion risks to ensure pipeline integrity. Introduction to DG-ICDA, objective of the DG-ICDA methodology, scope and applicability, key concept. Water presence and accumulation, overview of the four-step DG-ICDA process. Step 1. Pre-assessment. Step 2. Indirect inspection. Step 3. Direct examination. Step 4. Post-assessment, advantages of DG-ICDA, limitations and key assumptions, conclusion and key takeaways. The Internal Corrosion Direct Assessment Methodology for pipelines carrying normally dry natural gas, commonly referred to as DG-ICDA, is a structured and engineering-based process developed to proactively identify, assess, and manage the threat of internal corrosion. This methodology is formally documented in NACE SP0206 and is intended for pipelines that typically transport dry gas but may still be susceptible to localized internal corrosion due to intermittent or unexpected presence of free water. Although dry gas systems are generally considered low risk for internal corrosion, operational upsets, changes in gas composition, or inadequate dehydration can create conditions where corrosion becomes possible. DG-ICDA addresses this challenge by providing a systematic framework that allows operators to predict where corrosion is most likely to occur rather than relying solely on random inspections or reactive maintenance. The methodology emphasizes understanding pipeline design, operating conditions, gas quality, and historical performance to establish a defensible integrity assessment. DG-ICDA is particularly valuable because internal corrosion is often difficult to detect using conventional inline inspection tools in gas pipelines, especially when corrosion is localized. By focusing resources on the most susceptible locations, DG-ICDA improves safety, optimizes inspection costs, and supports regulatory compliance. This introductory slide establishes the purpose of DG-ICDA, its relevance to gas pipeline integrity management, and its role as a preventive rather than reactive corrosion control strategy. The primary objective of the DG-ICDA methodology is to identify and manage locations within normally dry natural gas pipelines where internal corrosion is most likely to initiate and progress. Rather than attempting to inspect an entire pipeline indiscriminately, DG-ICDA aims to focus attention on specific areas where free water may accumulate and remain in contact with the pipe wall. This objective is achieved by integrating engineering analysis, operational data, and corrosion science into a repeatable assessment process. DG-ICDA seeks to reduce uncertainty by systematically evaluating factors such as gas composition, operating pressure and temperature, pipeline elevation profile, flow regime, and historical upset conditions. Another key objective is to support informed decision-making related to inspection planning, maintenance activities, and mitigation measures such as improved dehydration, operational controls, or targeted repairs. By identifying corrosion-prone locations before significant damage occurs, DG-ICDA helps prevent leaks, unplanned outages, and safety incidents. Additionally, the methodology supports regulatory and industry expectations for proactive integrity management by providing documented justification for inspection intervals and locations. Ultimately, the objective of DG-ICDA is to enhance pipeline safety and reliability while optimizing the use of inspection and maintenance resources through a risk-informed, technically sound approach. DG-ICDA is specifically applicable to pipelines that transport normally dry natural gas, meaning systems where gas dehydration is designed and operated to prevent continuous free water presence. The methodology is not intended for pipelines that routinely transport wet gas, multiphase fluids, or liquids, as those systems are better addressed using alternative internal corrosion assessment methods. The scope of DG-ICDA includes both transmission and distribution pipelines, provided that sufficient data are available to support the assessment process. It applies to onshore pipelines and may be adapted for offshore applications with appropriate engineering judgment. DG-ICDA requires that operators have access to reliable information on pipeline design, materials, operating history, gas quality specifications, and corrosion control practices. The methodology is most effective when used as part of a comprehensive integrity management program rather than as a standalone activity. It is also important to recognize the limitations of DG-ICDA. It relies heavily on assumptions and modeling, and its accuracy depends on the quality of input data. Pipelines with significant data gaps or frequent liquid carryover may not be suitable candidates. This slide clarifies where DG-ICDA can be applied effectively and sets realistic expectations regarding its intended use and boundaries. The fundamental concept underlying DG-ICDA is that internal corrosion in normally dry gas pipelines can only occur if free water is present at the pipe wall for a sufficient duration. Even in dry gas systems, water can be introduced through operational upsets, inadequate dehydration, hydrostatic testing residues, or condensation due to temperature and pressure changes. Once water is present, it may accumulate in low points, sag bends, or areas with reduced gas velocity. DG-ICDA focuses on identifying these potential accumulation locations by analyzing the pipeline elevation profile and flow characteristics. The presence of corrosive species such as carbon dioxide, hydrogen sulfide, or oxygen further increases the corrosion risk when water is available. Understanding how and where water can enter, condense, and remain within the pipeline is therefore central to the methodology. This concept shifts the assessment focus from generalized corrosion risk to location-specific susceptibility. By predicting water holdup zones, operators can prioritize inspections where corrosion is most likely rather than assuming uniform risk along the pipeline. This slide emphasizes the critical role of water in internal corrosion and explains why DG-ICDA places such strong emphasis on hydraulic and topographical analysis. DG-ICDA is structured around a four-step process designed to systematically assess and manage internal corrosion threats. The first step, pre-assessment, determines whether DG-ICDA is applicable and whether sufficient data exist to proceed. The second step, indirect inspection, involves modeling and analysis to identify locations where internal corrosion is most likely based on water accumulation potential. The third step, direct examination, consists of physically inspecting selected sites to confirm the presence or absence of corrosion and to measure its severity. The final step, post-assessment, integrates inspection findings to refine corrosion predictions, evaluate pipeline integrity, and establish future actions. This structured approach ensures traceability, consistency, and technical rigor throughout the assessment. Each step builds upon the previous one, reducing uncertainty and improving confidence in the results. The four-step framework also supports continuous improvement, as results from direct examination and post-assessment can be fed back into future assessments. This slide provides a high-level roadmap of the DG-ICDA methodology, helping the audience understand how the individual components fit together into a cohesive integrity management process. The pre-assessment step is critical in determining whether DG-ICDA can be effectively applied to a given pipeline segment. During this phase, operators collect and review essential data related to pipeline design, construction materials, operating conditions, gas quality, and corrosion history. This includes information such as pipeline diameter, wall thickness, elevation profile, pressure and temperature ranges, dehydration performance, and historical upset events. The objective is to confirm that the pipeline is indeed normally dry and that internal corrosion is a credible but manageable threat. Pre-assessment also involves identifying data gaps and assessing whether they can be addressed through reasonable assumptions or additional data collection. If data quality is insufficient, DG-ICDA may not produce reliable results. Additionally, this step establishes assessment boundaries, defines analysis segments, and documents assumptions that will be used in later steps. By rigorously screening applicability and data readiness, the pre-assessment step ensures that resources are not expended on an assessment that lacks technical validity. This slide highlights the importance of preparation and data integrity in achieving meaningful DG-ICDA outcomes. Indirect inspection is the analytical core of the DG-ICDA methodology. In this step, collected data are used to model gas flow behavior, water condensation potential, and liquid holdup along the pipeline. The analysis typically incorporates elevation profiles, pressure and temperature gradients, and gas composition to predict where water is most likely to drop out of the gas stream and accumulate. Locations such as low points, uphill sections following sags, and areas of reduced flow velocity are given particular attention. The output of indirect inspection is a prioritized list of suspected corrosion locations ranked by relative likelihood and severity. This prioritization allows operators to focus direct examination activities on the most critical sites. While no physical inspection occurs during this step, the quality of the modeling directly influences the effectiveness of the overall assessment. Conservative assumptions are often used to ensure that high-risk locations are not overlooked. This slide explains how indirect inspection transforms raw data into actionable insights that guide targeted inspections. Direct examination involves physically inspecting selected pipeline locations identified during indirect inspection to confirm the presence and extent of internal corrosion. This may include excavation, removal of pipe sections, internal visual inspection, ultrasonic thickness measurements, or other suitable non-destructive examination techniques. The goal is to validate the predictive accuracy of the DG-ICDA model and to obtain quantitative data on corrosion damage. Site selection is critical, as only a limited number of locations are typically examined due to cost and operational constraints. Findings from direct examination provide essential feedback on corrosion mechanisms, rates, and distribution. If corrosion is found, its severity is assessed against applicable acceptance criteria to determine whether immediate repair or mitigation is required. If no corrosion is found, confidence in the model assumptions may be increased. This step represents the point where analytical predictions are tested against real-world conditions, making it a cornerstone of the DG-ICDA process. The post-assessment step integrates the results of direct examination with the original DG-ICDA predictions to draw conclusions about pipeline integrity and future risk. During this phase, operators evaluate whether the assessment objectives were met and whether the model accurately identified corrosion-prone locations. Any discrepancies between predicted and observed conditions are analyzed to improve future assessments. Post-assessment also involves determining appropriate mitigation actions, such as repairs, operational changes, enhanced monitoring, or improvements to dehydration systems. Additionally, the results are used to establish reassessment intervals and inspection plans based on demonstrated risk. Thorough documentation is essential to support internal decision-making and external regulatory review. This step ensures that DG-ICDA is not a one-time exercise but part of a continuous integrity management cycle. The slide emphasizes learning, validation, and continuous improvement as key outcomes of post-assessment. DG-ICDA offers several significant advantages for managing internal corrosion in normally dry gas pipelines. One of the primary benefits is its targeted approach, which allows operators to focus inspection and maintenance resources on the most susceptible locations rather than inspecting entire pipelines indiscriminately. This results in cost savings and reduced operational disruption. DG-ICDA is also flexible and can be adapted to a wide range of pipeline configurations and operating conditions. The methodology encourages a deep understanding of system behavior, promoting better operational practices and data management. Additionally, DG-ICDA provides a structured and documented process that supports regulatory compliance and audit readiness. By identifying corrosion threats early, the methodology helps prevent leaks, improve safety, and extend pipeline service life. This slide summarizes why DG-ICDA is a valuable tool within a comprehensive pipeline integrity management program. Despite its benefits, DG-ICDA has limitations that must be clearly understood. The methodology relies heavily on the quality and completeness of input data, and inaccurate or missing information can lead to incorrect conclusions. DG-ICDA also depends on modeling and assumptions regarding water behavior and corrosion mechanisms, which introduces uncertainty. It may not be suitable for pipelines with frequent liquid carryover, complex multi-phase flow, or highly variable operating conditions. Engineering judgment plays a significant role in interpreting results, meaning outcomes can vary between practitioners. Additionally, DG-ICDA does not eliminate the need for other integrity tools and should be used in conjunction with monitoring, operational controls, and corrosion mitigation programs. This slide reinforces the importance of understanding the assumptions and limitations to ensure DG-ICDA is applied appropriately and responsibly. DG-ICDA is a proactive, systematic methodology designed to manage the internal corrosion threat in normally dry natural gas pipelines. By focusing on the conditions required for corrosion, particularly the presence and accumulation of water, it enables operators to identify and prioritize high-risk locations with greater confidence. The four-step process of pre-assessment, indirect inspection, direct examination, and post-assessment provides a logical and defensible framework for integrity decision-making. When applied correctly, DG-ICDA enhances safety, optimizes inspection resources, and supports regulatory compliance. However, its effectiveness depends on high-quality data, sound engineering judgment, and integration with broader integrity management practices. The key takeaway is that DG-ICDA is not merely an inspection technique but a comprehensive assessment philosophy that emphasizes understanding, prediction, and continuous improvement in pipeline corrosion management.